Hello there and welcome again to another episode of Darko's Game Dev Cookbook, and in today's tutorial we're going to be talking about Phong shading. Phong shading is going to enable us to have better lighting, better looking lighting. It's going to look much more real, and it's going to introduce a few concepts like ambient light and materials, which is super cool. So let's get started. The first concept we need to learn in this tutorial is ambient light. What is ambient light? If you imagine that this sphere is in a 3D space, let's say a 3D box, and there's a light coming in that box, the light is going to be bouncing around the place, and some of the rays of the light would land on this sphere. Although they're not directly hitting the sphere, they would be indirectly hitting the sphere, in this example from this side that's now completely blank, which means that in this case even the part that's blank would be lit to some extent, and it's going to depend on the material how much that ambient light is going to affect the sphere or an object you have. And I have some things to show you first. I think this is quite good. So the first thing I said, there is ambient light, right? Ambient light is gonna be something like, it's gonna be some form of a constant we're gonna apply on top of our color to make your color more intense, and that will cause the darker parts of your sphere to become lighter, and that's the easiest part to do. So first we're going to be doing that, and then we're going to move to the cooler parts, diffuse and specular props of our sphere or material. We're going to define a material, and we're going to define how much diffuse or specular that material is. So in short, if your material is 100% specular, that's basically a full mirror. And what Phong does, it has these three components, because in the end you're going to end up with a layer that would look like this, which is the diffuse layer, this one over here. The specular layer is this one. It's basically the shiny thing you see that reflects directly, which means that the light would, like in this component, the light, basically this thing you see here reflected is the light itself, and it reflects perfectly back to your eye. So with these on top of each other, you will get this diffuse and specular look of your sphere, and then on top of that you have this ambient light that would light the parts of the sphere that are in complete dark in regards to your lighting you have in your scene, but are still lit because of it. So let's first start with ambient light, and then we're gonna see what we can do with diffuse and specular properties of our material. Let's first define a material. So material is basically something you're gonna apply to your sphere. And your material for now is gonna have only one prop, which is gonna be the strength of the ambient light it's gonna be exposed to, kind of. Cool. And now we can define over here, say, I'm gonna set it to 0.2 and not any higher number, because you'll soon realize that this is gonna add up on your color. So your color is a vector that has R, G, and B defined, and R, G, and B go from 0 to 1. So if you, let's say, put this ambience to 2.0, it's gonna look super lit, not in a good way. I mean, it's not the thing you want. With ambient light, you want this subtle light to be visible. So I usually go for numbers that are super low. I'm gonna put it to 0.2 and probably tweak it later on. We have our material now. That's good. What do? We go back to the place where we do this intersections, and where we apply our color. If you remember from the last tutorial, we had this coefficient thing that was a dot product between the light direction and the surface normal, and that's how we got this one. But now we want to spice it up. We want to add some color to it, so we have this ambient light on top of that, applying its own value. So we're going to do this. we have the ambience strength, and then we have the sphere color. And then we add those two. So if I run it, I think it compiled well, that's cool. You probably haven't noticed immediately what happened, but let me just do this and compile. As you can see, the whole sphere is now much more lit. It looks light. The parts that were lit already before are more lit because we're applying this ambient light on top of that. And then the parts of the sphere that were completely black are actually now they have some value now. So if you do this as we did in the previous one, it still behaves the same way. It's just much more lit. And in this case, that would mean that there is some light that's super strong, and it's going in your 3D box your sphere is in, and it's bouncing back and forth between the boundaries of your box, and it's resulting in this light. And you don't want this ambient light to be this big, in this scenario at least. We can put it to 0.4 just to get it highlight the sphere a bit more. So it already looks better than the previous tutorial. I'm gonna do this actually. Just a short comparison of what we did with a few lines of code. This is our sphere now, and this is what it looked like. And you can already see that it looks a bit more realistic to some extent. However, it's not much we can do with realism with a sphere that's jumping in an empty space, but it looks a bit more alive. Okay, and this is just ambient light, and we have a lot of things to do before we can say this is good and this is done. So as I said before, ambient light, check, we have that. Now we gotta sort out the diffusal and the specular component of this thing. And to be able to decode what diffusal is what you see in the previous example we did over here. So this is diffusal light. There is no direct reflection coming in. You see light that's based on the dot product of normal of your sphere and the light that comes in. There is no anything spectacular. Like, it doesn't depend on where your eye is pretty much. It depends where the light is and depends on the surface normal. So your eye is not really important factor in this case. Pretty much, and with specular component, it's important because the thing that's reflecting from that sphere, it's gonna pretty much depend where you are to see that light. You would see different things in the sphere if you move, right? So for diffuse light or diffuse prop or component, the only thing that's important, as I said, is the direction of the light itself and the direction of the surface normal from the sphere itself. So diffusal light looks like this. There is a ray that comes from the light source, and it jumps randomly somewhere. It can be your eye, it can be anything else, any direction really. It's semi-random. And then the more diffuse a material is, it's gonna do this more randomly. It's gonna look more diffuse. It's gonna look more blurred in a sense. It's not gonna reflect it directly. So let's try to do this diffusal model in our code, and that should be fairly straightforward. So let's say we have, and of course I need to open up the right tab first. Let's say we have a property of this material that's diffuse, and that's going to be the coefficient of how much we diffuse. And we're going to say here, and I don't know, let's put it to 0.4. I have no idea how this is going to look like just by looking at the numbers, really, but let's try it out and see how it works. So our diffuse coefficient, if you go back again, the thing I didn't mention, the diffuse itself is gonna be this dot product between light direction and surface normal, which is actually what we have and we had from previous lesson. So if we go back to our thing over here, you're gonna notice that this coefficient is pretty much the thing we want there. That's the dot product between the light direction and surface normal. So this coefficient is something that we already have in place to make this thing work. So we can do coefficient. So this part, it goes away because we are not using the old model, but we're gonna use it now in a different way with some material props. So we're gonna say coefficient, which is gonna be this one, right? And then we're gonna do it's gonna be this one, and then we need to multiply it by a certain factor, which is your material factor. So how do you do that? Well, yeah, easy peasy. We go here. Where am I? Coefficient. We say material diffuse times coefficient, and if we compile that, we get this thing. So why does this thing look like this? Well, material diffuse is obviously 0.4. It's gonna fiddle with the color itself. We are missing something. What are we missing? We are missing sphere color. Sphere color. So these two numbers together give us a weight of the color of the sphere at certain points, which means that all of this needs to be multiplied by sphere, like this. And if we do that, we do have some behavior that looks better, right? Now it looks bland because the ambient light is there plus diffusal, and the difference between colors in the dark side and the light side of the sphere are not that pronounced. What we can do to make it better at this point, we can make the ambience look a bit more dark, and then we can diffuse more. And then now we have the same thing as we had before. So the thing I didn't explicitly state here is the color part, and it's important that you keep that color part. We just multiply it with there, because without it, you're just getting random colors, right? We could possibly maybe do this just so people know that this is diffuse. This is how much we diffuse. Then we have the specular prop as well. We're gonna leave it at 0 for now, and we're gonna replace this one with this one, so we see all the components nicely done there. Also, we have this ambience thing, material diffuse. That's cool. So we can do and replace this as well with ambient. Boom, and then we have ambient plus diffuse. Yes, of course, this is the result of this is of course not a float, it's a color, which means that we need to use a vector for that color. And this is also a vector, so we can stash it like this. Fine, so we have this thing that looks the same as it looked before, and now the magic starts. The specular part says, or it depends on where you are, where your eye is. It depends on the angle of the light that goes in that goes in a certain angle to your sphere, and then that light bounces back in some direction. If that light bounces back to your eye directly, that means that whatever was bouncing, you see that thing there. So if you had a mirror and you shoot the ray in the mirror and it bounces back straight into your self, you see yourself, right? Pretty much same thing happens here. It's just like a mirror prop of this material, which means that basically what this photo displays over here, this ray is going to shoot the mirror and it's going to enter in a certain angle and go back. If you see this ray with your eye, that means that you see this thing over here. However, there is with this Phong shading model right now, we are not reflecting real objects, we are reflecting only light. We want to make it look specular and have that have this dot over here that is going to make it more realistic. In future tutorials, we're going to make real reflection models, and we're going to try to blend colors and display different objects around you as well, and that's going to be super interesting. So I think you should stay tuned for that part as well. But right now, let's just make the specular component of this sphere so we have it. Specular component is slightly different from the diffuse component. The reason for this is simple. So if you have if you have these two vectors that are important, so your eye to the surface and light to the surface, those two vectors are important. That means that if the light hits this spot and goes to your eye, you see it. If it hits this spot and goes to your eye, you see it, and so on. If you use this normal calculation of U direction and light direction, the circle you see here as the light shine, kind of, without this special thingy around it, it would be super wide in some, it would look super wide. So we need a way to control how shiny your object is as well. So it does reflect it, that's fine, but it also needs to define how shiny that glow is gonna be. And you're gonna see in a moment how this works and how you can control it with this thing over here. So you will still bounce back some beams of light to your eye. You're gonna see that light. It's not gonna be like just a circle that's gonna be unified. But with this, if you do this, if you do to the power of shininess, you're gonna have this cosinus angle that's created between these two rays. It's gonna drop significantly faster if you do this thing over here, if you go to the power of something. And that was the whole idea of when Fog this model. That was the idea behind shininess. But let's go to code. I'm gonna make one version without this, and then we're gonna make a version with this, and you're gonna realize why this works like this. So if we go back to our code, the thing we are missing is the specular component here. And we're gonna say that our material is 0.5 specular. We're gonna play with this number later on, just to see how it behaves. And let's go here and say that our specular is material dot specular times what? Let's go back to the formula. So we have light direction and view direction. So light direction and view direction. You'll also notice one important thing. The view direction in this this is a picture I took online from the Phong model description. The vector we have goes from the surface of the sphere or an object to your eye. It doesn't go in the opposite direction. And you'll see that when we have our camera or our eye in this code we wrote, that our direction goes to the sphere. So it's the opposite direction from this one. We're gonna correct that in an easy way. You can just make it negative pretty much, and it does the same thing you want. So let's go back to code. We said light direction and viewer or view direction. What do we have from our data before? So we should have our direction. Direction is, what did we say? This one. So okay, this direction is our camera or our eye direction. And let's say we have a dot product of our direction. And the other beam is the beam of light or direction of light. So where is that? Well, that's here. Right? So if we go back to this model, this direction and this direction, they create a certain angle. And then we have sphere color. I did this and nothing happened because I didn't do this. And now all of a sudden we do, of course, it looks lighter because obviously we're adding color. But what we can do, we can try playing with parameters a bit just to see how much it changes. So if we do this, you'll see that whatever you do here, really, even if you go to 0.9, it doesn't bring that tiny circle that's super shiny, that looks like glow, that it shines. You don't see it because the cosinus angle is gonna go from the value of cosinus angle is going to be go from 1 to 0, but it's going to go gradually from 1 in the center to 0 at the point where the surface normal and light normal are hitting 90-degree angle, which means that at this point over here, it's gonna be 1 and it's gonna be the brightest, but at this point over here, it's gonna be 90 and it's gonna be 0. So what did we add with this specular thing with this here? Well, we didn't add anything really. I mean, it's just added another diffuse that behaves slightly differently because we are doing dot product between different vectors right now. So yeah, we move around. Sure, this is gonna apply this light to different parts of the sphere. As we move around, it's gonna calculate the angle of our direction and light, and it's gonna do slightly different thing. But it's not the thing we want. So what Phong did, he said, well, if I go from 1 to 0 like this, what if I do that 1 to 0 transition more quickly? What if I, whatever the result of that product is, what if I bring it up to a certain power so it goes down to 0 quickly from 1 to 0? And that's what happens here. So you have this shiny dot that can be of any size, and you control it with the shininess factor we saw over here. So instead of setting our math just by this regular dot direction thing over here, we're gonna bring this to a certain power. First things first, we can do this. And let's add another thing to our material. Let's say that our material has something called shininess. And let's add that thing here. And let's say that our shininess is 5. This time, this number is probably going to be all right. We'll tweak it, but empirically wise, it should be okay. And then if we go back here, we say we will write this instead. And now you can already see, even as it jumps a bit, look, as it jumps a bit up and down, you can see differences in what part of the sphere, how the sphere is getting shined. Yeah, I realized that I missed one thing over here. So in this example over here, I'm talking about light direction and dot product between line direction and view direction. It's not actually it's not view and light direction that are important. The thing we want to see this reflected light and this viewer vector. We want to see the angle between those two, because that means that will give you the approximation of how much this reflected light differs from how far it hit from your eye, pretty much. And then depending on that, it's gonna give more or less weight to this model. So let's go back here and fix this thing real quick. There is a built-in function in GLSL that you can use to reflect a ray, and you can reflect it from a using a few parameters, which is the incoming ray, the normal over which you're reflecting. So in this case, you're going to have your surface, you're going to have the incoming ray, you're going to take this normal over here and going to get this ray over here. And then once you have that ray that's reflected from that surface, in this case this sphere, you're going to have this angle over here, or a number that is a dot product of these two vectors, and then that number is going to be important for your calculations, because right now you'll see it doesn't behave really how you would want it to behave. Let's fix it. So light direction, we're going to do reflect. That's the built-in function I was talking about just a moment ago. And what you do, you take this direction and you reflect it against the surface, or you give it the normal of the surface you're reflecting against, and then that's how you get that reflected ray. And our surface normal is already defined up there, so we can do this. And we want to reflect it here. And now we have this thing. Look at this. It does exactly the opposite thing of what we wanted it to do. And as I said, again, your reflected ray and your camera direction right now are pointing in different directions, which means that this dot product is gonna be a negative number. That's not the thing we really want to do. So we're gonna invert it, and as soon as you invert it, you get a different kind of behavior. So let's go back for anyone who might not still get what's happening. Our vector goes from viewer to surface normal, our direction, and this light over here, it goes from this to this. So, or actually this viewer direction in this model, they should go in the same direction. So that's how you do it. You just invert it, and now you have this sphere that looks kind of shiny, you know. It's not that bad, but now, as I said before, you have this material shininess you can play with. And let's see what happens when we add, let's say, 7. It looks like this. It looks weird. Why does it look like this? Why is part of the this sphere completely gone? Well, there is a catch over here as well. So it can happen if this direction and the reflected ray, if this turns to be negative, then you're in a problem. Then your sphere looks chopped. I mean, it looks cool. You can still, like, if you want to be cool, you can keep it like this. But what you need to do in this case, you need to control what is being outputted here. We don't want this shininess thing to affect our colors, so the color disappears. The shininess thing is just an addition on top of this, right? So what we're gonna do, first we're gonna do, we should probably tidy this up a bit so it's more obvious what's happening. So I'm gonna extract this power thing here, and we're gonna say float shininess equals this one. Let me see. Okay, still the same behavior, expected. Okay, so we want this result over here to be something that is that cannot go in a negative direction over here, because if it goes in a negative direction, then we're gonna have this problem over here. When we do these calculations, we're gonna basically return 0 in this case. So we need to know that this dot product that affects shininess needs to be at least 0 or higher. Everything that bounces behind or in some weird way, it should not do this. It should not crop the sphere. You should still leave the original values there. So what you do, you say max, like this, and now whatever is here, it's like the worst case scenario. We're gonna end up with a 0 over here. And what that means that, okay, it's gonna take the dot product. If this is negative, this whole thing is gonna be 0. So this is what you do. And now you have this shiny looking sphere over here. What you can do, you can play with shininess. And if you set it to 15, for example, you'll notice that the sphere becomes smaller. The shinier it is, the light is gonna disperse less, so it's gonna look like it's more reflective. It's gonna look like it's just going straight to your eye. And basically this is just a hack to make it look real. This doesn't really resemble the real world that much. It's a really good mathematical model and approximation, and there's a lot of other models. We can talk about those later at some point, but this model gives you this feeling of shininess. It gives you this feeling of the light really hitting the sphere, and you know, if you have, for example, if you're making a pinball game and you want to make those pinball balls shiny, this is probably something that will give you some the touch of it. And also, as I said, this thing over here, it doesn't have any real reflections per se. So if we had another sphere in the scene, the light that falls into this sphere or any rays that fall into the sphere you wouldn't see the other sphere in it. You would just see the light. So it's not really reflecting anything at this point. But what we're gonna do in the next tutorial, we're gonna do some real reflections. Reflections are a complicated subject, can be a complicated subject. We're gonna make it simple again. We're gonna make a simple scene with this sphere, and we're gonna add another sphere, and then we're gonna make them reflect each other, and you'll see how deep reflections can go, how the reflections can go many levels recursively and so on. And we're going to try to make it so that our ray tracer is not spinning 60 FPS anymore. So we see how far this goes and how much recursion you can get, or not really recursion in this case, but we'll see what we can do. We can try many levels as we want. So yeah, this sphere is nicely done. Pretty much. The thing with Phong shading though is the thing we did with these calculations over here. They do not split colors in separate channels per se. So you can choose to have a red channel reflect more. It's easy. You just separate the color calculations per colors and then blend them all in together, and then all of a sudden only the red part of your sphere is reflecting more, or there is more red reflections or reflections shown in the red channel. But it's not important for this specific scenario, because this is just a sphere of one color and it doesn't have any pooled reflections whatsoever. Another thing that I wanted to do, since I do that every time we do this, this is the sphere we had before and this is the sphere we have now. So it's not super different, but we do have the specular component on top of it right now, so it looks like it's glowing. And you can tweak these parameters as much as you want. The thing is, if we make it less specular, it's going to affect the specularity as well. So if you go 0.4, the size of the circle of light will still stay the same, but it will be less intensive. And another thing worth mentioning is that your light can also have a color. So you can have a light that's not white, you can have red light. And then when we do these calculations down there, you also, besides using this sphere color that we use over here, we need to blend in the light color as well. And then depending on how reflective your material is gonna pick up more or less of that color. And the original Phong model actually deals with this as well. And it basically just multiplies that light color with this color pretty much. And another thing that I just realized in the meantime as well, and it's worth mentioning. So the coefficient, from the previous tutorials, coefficient itself you get here is the dot product between surface normal and the light direction, right? So there is parts of this calculation as well that can turn out to be negative. Why? Because these vectors can go in the same direction. For example, in the part of the sphere that's over here, if the light is going this way, that means that it's gonna this vector that goes from this surface over here is gonna go in the same way, and that's gonna make the dot product negative. And then when you calculate this diffuse light over here, it's gonna look like it's gonna be negative, and that negative number, when you do this plus 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 over here, is gonna do weird things with your sphere. Really, the color, it's not the thing you want. So the thing you need to add is this max coefficient 0, which is gonna clamp your whatever value you get to 0. It's always gonna be at least 0. It's not gonna go negative. And I'm gonna show you what this does. So if I remove this thing over here and press play, this is how your sphere looks like with these calculations. And you can see that this area is again completely blank. So the ambient light is cancelled out at this point pretty much. I mean, if you do change this ambient light to some higher number, you will see the effects, just because it's this dot product is not negative enough to affect it. But you want to have this ambient light super discrete. So what you do, you basically take this coefficient and you nail it down so it's always at least 0. And when you do this and press play, you can see that your sphere looks much better. And now this sphere area over here is actually ambient light acting on it and doing it and making it lit like it is. It looks pretty cool. And now you have the specular component, and you feel free to play with the shininess as well. I think it's quite fun. So if you do shininess 4, it spreads out. If you do shininess 1000, it's super little, and so on. And then you can also play with these components here. You can make it super specular. Let's make it super specular. Okay, And that's about it. This is for all for this Phong shading tutorial. If you want to do reading and you want to learn more about this model mathematically speaking, since I haven't gone into super deep parts of it, it doesn't really go that deep, but I'm gonna leave a link down below. I found a really good web page, and actually a few of them with some of the resources you can use to make it real. And in the next tutorial, as I said, we're going to do some reflections, and we're going to do some real reflections of objects. You're going to see two spheres in the scene, and they're going to be reflecting each other in real time, and we're going to do reflections in several levels, so you will see reflections in reflections possibly as well. So yeah, until the next time, stay safe and goodbye.